You can predict where a planet will be, not approximately, precisely. Give an astronomer the mass of a star, the distance of a planet, and Newton's laws, and they'll tell you where that planet will be in 100 years, 1,000 years, 10,000 years. They'll calculate its orbital speed to the meter per second. They'll predict when it will transit across the star's face. They'll get it right. This works because gravity behaves exactly as we expect it to. The equations Newton wrote in 1687 describe how massive objects pull on each other across empty space. Einstein refined these equations in 1915, accounting for extreme conditions Newton never imagined. But for most cosmic situations, planets orbiting stars, moons orbiting planets, Newton's version works perfectly. We've sent probes to the outer solar system using these equations. They arrive on schedule. The logic is straightforward. A planet orbits because gravity pulls it toward the star, while its sideways motion keeps it from falling in. The balance between these two effects determines orbital speed. Close to the star, where gravity is strong, planets move fast. Far from the star, where gravity weakens, planets move slowly. Mercury screams around the Sun at 47 kilometers per second. Neptune, 30 times farther out, crawls at 5 kilometers per second. The mathematics is simple. Orbital velocity decreases with the square root of distance. Double the distance and velocity drops by about 30%. This relationship, this inverse relationship between distance and speed, is called a Keplerian decline. It's not a theory, it's not a model, it's what gravity demands. We see this pattern everywhere we look. Saturn's rings follow it, Jupiter's moons follow it, the planets follow it. Every system where most of the mass sits at the center follows it. The universe obeys Kepler's laws. Until you look at galaxies. In 1970, astronomer Vera Rubin pointed a spectrograph at the Andromeda galaxy. She wanted to measure how fast stars were orbiting the galactic center at different distances. The work was tedious. Each star's light had to be captured, its spectrum analyzed, its velocity calculated from the Doppler shift of its spectral lines. She expected to find what gravity predicts. She expected to confirm what decades of astronomical observations had already shown, that galaxies, like solar systems, follow Kepler's laws. She found something else. Stars at the edge of Andromeda were moving just as fast as stars near the center, not approximately as fast, the same speed. The velocity curve was flat. Stars 50,000 light-years from the galactic core were orbiting at the same velocity as stars 10,000 light-years out. This made no sense. The outer stars should have been moving much slower. They should have been crawling. Instead, they were racing. Rubin checked her measurements. She calibrated her instruments. She analyzed different galaxies. She found the same result every time. The velocity curves were flat. Galaxies were rotating wrong. This wasn't a small discrepancy. The outer stars were moving 2, 3, sometimes 4 times faster than they should have been. If you calculated how fast these stars needed to move to stay in orbit, given the visible mass of the galaxy, they were exceeding that speed dramatically. They were moving so fast they should have been flung out into intergalactic space. They should have escaped. But they hadn't. They were still there, orbiting peacefully, as if held by something invisible. Other astronomers confirmed Rubin's findings. Radio telescopes detected hydrogen gas at the edges of galaxies, far beyond where most stars end. That gas was also rotating too fast. The pattern held for spiral galaxies, elliptical galaxies, dwarf galaxies. Every rotating galaxy we've measured shows the same problem. They all rotate wrong. The discrepancy isn't subtle, it's enormous. When you add up all the visible matter in a galaxy, all the stars, all the gas, all the dust, everything we can see with telescopes, you get maybe 10 or 15% of the mass needed to explain the rotation. The other 85 to 90% is missing. It's not dim, it's not hidden behind something, it's simply not there. Or rather, it's not there in any form we can detect with light. Two possibilities present themselves. Either there's matter we can't see, or gravity doesn't work the way we think it does. Either galaxies contain vast amounts of invisible mass, or Einstein and Newton were wrong about how gravity behaves on galactic scales. Both options demand evidence. Both require explanation. Neither is comfortable.
Gravity's behavior has been tested extensively. We understand it well in the solar system. Newton's inverse square law, the rule that gravity weakens with the square of distance, has been verified thousands of times. Drop a ball on Earth and it falls exactly as Newton predicted. Send a probe to Jupiter and it arrives exactly where Newtonian mechanics says it should. Measure Mercury's orbit with precision, and Einstein's corrections account for the tiny deviations Newton couldn't explain. But those tests occur at relatively small scales. The distance from Earth to the Sun is 150 million kilometers. The distance from the Sun to Neptune is 4.5 billion kilometers. Large numbers, but nothing compared to galactic distances. The distance from the Sun to the center of our galaxy is about 260 quadrillion kilometers. That's 60,000 times farther than Neptune's orbit. We've never tested gravity at those scales in a controlled way. We can't. We can only observe. We see galaxies rotating, and we infer what must be true about gravity and mass. The question is whether our inferences are correct. Fritz Zwicky noticed the problem earlier than Rubin, in 1933, though his discovery involved galaxy clusters rather than individual galaxies. Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast individual galaxies were moving through the cluster by analyzing their Doppler shifts. He then estimated the cluster's total mass based on how much light it was emitting. The galaxies were moving too fast, much too fast. If the cluster contained only the mass Zwicky could see, the galaxies should have been moving about 7 times slower than they actually were. The cluster should have flown apart billions of years ago. The fact that it hadn't meant something was holding it together. Zwicky calculated that the cluster needed about 400 times more mass than he could account for with visible matter. He called this missing mass dunkle materia, dark matter. The name stuck, though Zwicky himself was skeptical of his own conclusion. He suspected there might be ordinary matter he couldn't see, dim stars, cold gas, black holes, or some other conventional explanation. For decades, most astronomers agreed. Dark matter was a curiosity, a puzzle, but not a crisis. Perhaps Zwicky's mass estimates were wrong. Perhaps there was simply more ordinary matter than telescopes could detect. Rubin's observations changed that. She wasn't looking at galaxy clusters, where measuring mass is difficult and indirect. She was looking at individual galaxies, measuring the speeds of stars and gas at different distances from the center. The rotation curves she found couldn't be explained away by dim stars or hidden gas. Something else was going on. The numbers were stark. In a typical spiral galaxy, visible matter accounts for perhaps 60 billion solar masses. The rotation curves suggest the galaxy contains 600 billion solar masses. The ratio varies from galaxy to galaxy, but the pattern is consistent. About 90% of the mass is invisible. Where could this mass be? Not in stars. We can count stars and measure their masses. Not in gas clouds.
Radio telescopes detect hydrogen and other gases throughout galaxies. Not in dust. Dust blocks light, and we can see its effects. Not in black holes, unless there are millions of them scattered throughout every galaxy, and we have no evidence for that. Not in any known form of matter. The situation grew stranger in the 1980s when astronomers began mapping how dark matter must be distributed. If dark matter exists, it can't be concentrated in the galactic disk where stars and gas reside. That wouldn't produce flat rotation curves. The dark matter must extend far beyond the visible galaxy, forming a spherical halo that dwarfs the luminous parts we can see. The galaxy we see with telescopes, the spiral arms, the central bulge, the glowing regions of star formation, is a small island of light floating in an enormous invisible ocean. This picture is unsettling. It means most of the galaxy is invisible to us. It means we're living inside something we can't detect directly. It means when we look at a photograph of a galaxy, we're seeing a tiny fraction of what's actually there. Feynman never wrote extensively about dark matter, but he understood the problem. In the 1980s, physicists were beginning to take it seriously, and Feynman was aware of the rotation curve measurements. He approached it the way he approached every mystery, by questioning assumptions and demanding clarity. What do we actually know? What are we inferring? What are we guessing? We know galaxies rotate. We know how fast they rotate at different distances. We know how much light they emit. We know the relationship between mass and light for stars. From these facts, we infer that galaxies contain more mass than we can account for. But inference depends on assumptions. We assume gravity works the same way at galactic scales as it does in the solar system. We assume stars emit light in proportion to their mass the same way they do nearby. We assume we're not missing something obvious about how galaxies work. Any of these assumptions could be wrong. The standard approach in physics is to keep the laws and add new entities. When Neptune's gravitational pull was disrupting Uranus's orbit, astronomers didn't change Newton's laws. They predicted the existence of another planet. They looked for it. They found it. The mathematics worked. The same reasoning applies to dark matter. Galaxies rotate wrong if we count only visible matter. But if we add invisible matter in the right amounts and distributions, the rotation curves make sense. The mathematics works. The galaxies stay intact. This approach requires dark matter to have specific properties. It must interact gravitationally, otherwise it couldn't hold galaxies together. It must not interact electromagnetically, otherwise we'd see it. It must be stable over billions of years. It must not clump into dense objects the way ordinary matter does. It must form smooth, extended halos around galaxies. These requirements rule out most forms of ordinary matter. Ordinary matter, protons, neutrons, electrons, interacts through all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Anything made of ordinary matter either emits light, absorbs light, or interacts with matter that does. We'd detect it somehow. Particle physicists began proposing alternatives. Perhaps dark matter consists of particles that interact only through gravity and the weak nuclear force. Such particles would be nearly invisible. They'd pass through ordinary matter without interacting. They'd form halos around galaxies because gravity would pull them together, but they wouldn't collapse into dense structures because they couldn't radiate energy away through electromagnetic interactions. These hypothetical particles became known as WIMPs, weakly interacting massive particles. The name is unfortunate but descriptive. WIMPs would have mass, giving them gravitational pull, but they'd interact so weakly with ordinary matter that detecting them would be extraordinarily difficult. A WIMP could pass through the entire Earth without hitting a single atom. The appeal of WIMPs is that they solve multiple problems simultaneously. They explain galaxy rotation curves. They explain why galaxy clusters don't fly apart. They explain observations of gravitational lensing, where the path of light bends around massive objects. They explain the cosmic microwave background's temperature fluctuations. They explain how galaxies formed in the early universe. A single type of particle, never directly observed, explains dozens of otherwise unrelated phenomena. This makes physicists nervous. Any theory that explains too much becomes unfalsifiable. If dark matter can be invoked to explain every gravitational anomaly, how do we test whether it's real? How do we distinguish between dark matter exists and we don't understand gravity? Experiments to detect dark matter have been running for decades. They're located deep underground to shield them from cosmic rays. They use ultra-pure materials, cooled to near absolute zero. They watch for the rare collision between a WIMP and an atomic nucleus in a detector. Such a collision would deposit a tiny amount of energy, a few thousandths of an electron volt, but it would be detectable. No experiment has found conclusive evidence. The Large Hadron Collider has searched for dark matter particles. Nothing. Direct detection experiments like Xenon and Lux have run for years. Nothing. Indirect detection experiments looking for dark matter annihilation in space. Nothing. The null results don't prove dark matter doesn't exist. They prove that if it does exist, it's even harder to detect than we thought. The particles could be heavier than expected. They could interact even more weakly. They could exist but remain forever beyond our experimental reach. This is where the situation stands. We have overwhelming evidence that galaxies contain more mass than we can see. We have a theoretical framework, WIMPs or similar particles, that would explain this mass, but we have no direct detection despite decades of effort. The alternative is to change gravity itself. Several physicists have proposed this. The most developed version is called Modified Newtonian Dynamics, or MOND, created by Israeli physicist Mordechai Milgram in 1983. Milgram noticed something peculiar about the rotation curve problem. The discrepancy between observed and predicted velocities always appeared at the same acceleration threshold, regardless of galaxy size. In regions where stars experienced acceleration less than about 10 to the minus 10 meters per second squared, Newton's laws started failing. Above that threshold, Newton's laws worked perfectly. This threshold is tiny. For comparison, Earth's gravitational acceleration at the surface is about 10 meters per second squared, 10 billion times larger. But the consistency of this threshold across different galaxies suggested something fundamental. Perhaps Newton's laws break down at extremely low accelerations. Perhaps gravity doesn't decrease with distance exactly as Newton claimed when accelerations are weak enough. Milgram proposed a modification. At high accelerations, gravity follows Newton's inverse square law. At very low accelerations, below the threshold, gravity weakens more slowly with distance. This change is small, but it's enough to explain flat rotation curves without invoking dark matter. MOND works remarkably well for spiral galaxies. It predicts rotation curves accurately. It explains the Tully-Fisher relation, an observed correlation between galaxy brightness and rotation speed that dark matter models struggle with. It does this with a single adjustable parameter, the acceleration threshold, rather than invoking an entire population of invisible particles with unknown properties. But MOND has problems. It doesn't work as well for galaxy clusters. It can't fully explain gravitational lensing observations. It struggles with the cosmic microwave background data. And most fundamentally, it's not a complete theory of gravity. It modifies Newton's laws, but doesn't provide a deeper principle from which those modifications emerge. It's a patch, not a framework. Several physicists have tried to develop relativistic versions of MOND that would replace or extend Einstein's general relativity.
These theories have technical names like TVs and conformal gravity. All face significant challenges. Constructing a modified gravity theory that matches Einstein's successes while fixing the galaxy rotation problem without introducing other inconsistencies has proven extremely difficult. The debate between dark matter and modified gravity continues. Both camps point to evidence supporting their view. Both camps point to problems with the other view. Neither side has delivered a knockout blow. What would Feynman make of this impasse? He'd likely insist on clarity about what we're actually observing versus what we're inferring. He'd push for experiments that could distinguish between the hypotheses. He'd be skeptical of theories that require too many adjustable parameters or that make predictions impossible to test. He'd also recognize that sometimes physics reaches a point where the answer isn't obvious. Quantum mechanics took decades to crystallize into a coherent framework. The nature of light as both particle and wave troubled physicists for centuries. Some problems don't yield to clever thought experiments or elegant mathematics. They require new observations, new technologies, new ways of probing reality. The galaxy rotation problem is one of those problems.
The implications expand beyond galaxies. If dark matter exists, it's the dominant form of matter in the universe. Ordinary matter, everything we can see, everything made of atoms, constitutes only about 15% of the total. We are the minority. The universe is mostly something else. This realization changes how we think about cosmic history. In the early universe, shortly after the Big Bang, dark matter would have outnumbered ordinary matter by the same ratio. As the universe expanded and cooled, dark matter clumped together first, forming gravitational wells. Ordinary matter fell into these wells, forming the first galaxies and stars. Structure in the universe, the distribution of galaxies, the cosmic web of filaments connecting them, is fundamentally a dark matter skeleton with ordinary matter draped over it. Simulations of cosmic structure formation using dark matter reproduce the observed distribution of galaxies remarkably well. Without dark matter, simulations produce a universe that looks nothing like what we observe. Galaxies form too late, cluster too weakly, and distribute too uniformly. Dark matter makes structure formation work. These simulations make specific predictions. They predict how many dwarf galaxies should orbit larger galaxies like the Milky Way. They predict how dense the centers of dark matter halos should be. They predict how dark matter should be distributed on very large scales. Some of these predictions match observations, others don't. The Milky Way appears to have fewer dwarf galaxies than simulations predict. Dark matter halos in simulations often have denser centers than observations suggest. These discrepancies could mean our simulations are incomplete, or they could mean dark matter doesn't behave exactly as we assume. Refinements continue. Perhaps dark matter particles interact with each other weakly, just not with ordinary matter. Perhaps there are multiple types of dark matter particles. Perhaps dark matter particles decay over time. Each variation changes the prediction slightly and might resolve some of the tensions between simulations and observations. But these refinements also make the dark matter hypothesis more complicated. What began as a simple idea, invisible matter that interacts only gravitationally, has evolved into a complex framework with multiple particle types, interaction strengths, and decay channels. At some point, the simplicity that made dark matter attractive starts to erode. Modified gravity advocates point to this complexity as evidence that we're on the wrong track. Science should explain more with less, not less with more. Adding invisible particles with carefully tuned properties to make the equations work feels like Ptolemaic epicycles, mathematical devices that fit the data without revealing underlying truth. Dark matter advocates counter that complexity is warranted when evidence demands it. Science physics is complex. The standard model includes dozens of particles with different masses, charges, and interaction strengths. Adding a few more particles to explain 85% of the matter in the universe doesn't seem unreasonable, especially when the alternative requires rewriting general relativity. The argument has been ongoing for 50 years. Neither side has convinced the other. Neither side has produced the decisive evidence that would settle the question. Recent observations have added new dimensions to the puzzle. In 2018, astronomers discovered a galaxy called NGC 1052-DF2. This galaxy appeared to contain almost no dark matter. Its stars were orbiting at exactly the speeds Newton's laws predict based on visible mass alone. No flat rotation curve, no missing mass, a galaxy behaving normally. If dark matter is a fundamental component of the universe, how does a galaxy form without it? If dark matter halos are the scaffolding on which galaxies build, why does NGC 1052-DF2 exist? The discovery sparked debate. Some astronomers questioned the distance measurements that led to the dark matter deficit. Others suggested the galaxy might have lost its dark matter through interactions with neighboring galaxies. Then, in 2019, astronomers found another similar galaxy, and another. At least a dozen dark matter-deficient galaxies have now been identified. They're rare, but they exist. They challenge the standard dark matter picture, while simultaneously challenging MOND. If modified gravity explains rotation curves, why do some galaxies still follow Newton's laws? Both camps scrambled to explain. Dark matter theorists proposed that these galaxies formed through unusual processes that stripped away their dark matter. MOND advocates suggested that in certain environments, the acceleration threshold might shift, making galaxies appear normal. Neither explanation is entirely satisfying. The universe seems to be resisting simple categorization. Some galaxies rotate wrong, some galaxies rotate correctly. Most show evidence of missing mass, a few don't. The pattern makes no sense under neither framework cleanly. Other observations point in other directions. Gravitational lensing, the bending of light around massive objects, provides an independent way to measure mass. When light from a distant galaxy passes near a closer galaxy cluster, it bends. The amount of bending depends on the mass of the cluster. Astronomers can map where mass is located by studying how light bends. These maps consistently show more mass than visible matter accounts for. The mass distribution matches what dark matter models predict. Light bends around empty regions of space where dark matter halos should be. The effect is too large to explain with modified gravity alone. One famous case is the Bullet Cluster, where two galaxy clusters collided and passed through each other. The hot gas in each cluster, visible in X-ray telescopes, collided and stayed near the collision site. But the gravitational lensing maps showed that most of the mass passed right through, unimpeded. The cluster's dark matter halos, unable to collide because they don't interact electromagnetically, sailed past each other while the ordinary matter crashed and stopped. This observation is difficult to explain without dark matter. Modified gravity can't easily separate mass from matter. Gravity comes from matter, so where matter goes, gravity should follow. But in the Bullet Cluster, gravity went one way and visible matter went another. Something invisible with mass passed through the collision. MOND advocates have proposed complex scenarios involving neutrinos or gravitational fields carrying momentum. The explanations are elaborate and require fine-tuning. Most physicists find the dark matter interpretation simpler. Yet, dark matter remains undetected. Decades of experiments, billions of dollars invested, no confirmed signal. The sensitivity of detectors has improved by orders of magnitude. The parameter space for WIMPs has shrunk dramatically.
If dark matter particles exist with properties anywhere near what was initially predicted, we should have found them by now. This forces dark matter theorists to consider alternatives. Perhaps dark matter isn't WIMPs. Perhaps it's axions, hypothetical particles originally proposed to solve a different problem in particle physics. Axions would be much lighter than WIMPs and interact even more weakly. Experiments to detect them require completely different techniques. Or perhaps dark matter is primordial black holes. Black holes formed in the first fraction of a second after the Big Bang. They wouldn't be made of any particle at all. They'd be concentrations of space-time curvature left over from quantum fluctuations in the early universe. They'd have gravity, but no electromagnetic signature. They could form dark matter halos without invoking new particles. Each alternative has its own challenges. Axion dark matter requires specific production mechanisms in the early universe that we can't directly observe. Primordial black holes would have affected Big Bang nucleosynthesis in ways we should be able to detect. Every candidate has problems. Every candidate requires assumptions. The situation is genuinely uncertain. We have strong evidence for phenomena we can't explain. We have competing frameworks, neither fully satisfactory. We have observations that support both sides and observations that trouble both sides. We're stuck.
This is uncomfortable for physics. The field prides itself on precision, on definitive answers, on theories that make predictions accurate to 10 decimal places. But the dark matter problem has resisted solution for nearly a century. It's not a small anomaly. It's not a minor correction to existing theory. It's a fundamental question about what most of the universe is made of, and we don't have a confident answer. Feynman once said that the highest form of understanding is knowing where our knowledge ends. He spent his career pushing at those boundaries, clarifying what we know and what we only think we know. The dark matter problem sits squarely at such a boundary. We know galaxies rotate wrong. We know something is missing from our models, but we don't know what. Some physicists find this situation intolerable. The answer must be findable. Either dark matter exists and we'll eventually detect it, or gravity needs modification and will eventually derive the correct theory. Persistence will yield results: better detectors, more sensitive instruments, cleverer experiments, deeper theoretical insights. One of these will crack the problem. Other physicists suspect we might be asking the wrong questions. Perhaps dark matter and modified gravity are both partial truths. Perhaps gravity behaves differently at galactic scales, and there's also some form of invisible matter. Perhaps the framework we're using, particles and forces, matter and space-time, is too limited to capture what's actually happening. Perhaps the universe is telling us something more profound than "there's matter we can't see," or "gravity works slightly differently." What could be more profound than that? We don't know. That's the point. When phenomena refuse to fit into our conceptual boxes, it often means the boxes themselves are inadequate. Quantum mechanics didn't emerge from trying to patch classical mechanics. It emerged from recognizing that classical mechanics was fundamentally wrong about reality. The quantum revolution required abandoning cherished assumptions about how nature works. The dark matter problem might demand something similar, not a patch to Newton's laws or a new particle in the Standard Model, but a reconceptualization of mass, gravity, or space-time itself. What that reconceptualization might look like is unclear. We're waiting for the next Einstein or Heisenberg or Feynman to see what we're missing. In the meantime, observations continue. New telescopes are mapping galaxy rotation curves with greater precision. Gravitational wave detectors are beginning to probe cosmic structure formation. Particle accelerators are pushing toward higher energies. Dark matter detection experiments are exploring new parameter spaces. Theoretical physicists are constructing new models, testing new ideas, searching for mathematical structures that might contain the answer. The work proceeds because the question matters. If 85% of the matter in the universe is something other than atoms, that's not a curiosity. It's the central fact about reality. Understanding what galaxies are made of is understanding what the universe is made of, and we don't understand it. Picture the Milky Way as you might see it from outside, a spiral disk of stars, gas, and dust glowing in the darkness of space. That disk is about 100,000 light-years across and contains 200 billion stars. It's beautiful, luminous, complex. Around that disk, invisible, extends something else, a spherical halo of dark matter reaching perhaps 500,000 light-years from the center. This halo contains most of the galaxy's mass. It's what holds everything together. Without it, the outer stars would escape, the spiral arms would dissolve, the galaxy would disintegrate. We live inside this structure. The Sun orbits 26,000 light-years from the galactic center, embedded in the dark matter halo. Dark matter particles, if they exist, are passing through Earth constantly, passing through your body constantly, right now as you read this. Billions of them every second, interacting with nothing, detectable only through their collective gravitational pull. Or perhaps there are no particles. Perhaps space itself behaves differently at these scales, curving in ways Einstein didn't predict, pulling on matter through mechanisms we haven't discovered. Perhaps what we call dark matter is actually a property of geometry, not substance. Either way, we're surrounded by something we don't understand. The galaxy we call home is mostly mystery. This should disturb us more than it does. We've mapped the human genome, we've photographed black holes, we've detected gravitational waves from colliding neutron stars billions of light-years away. But we don't know what most of our own galaxy is made of. We can calculate its effects precisely, predict how it influences galactic rotation, model how it shaped cosmic structure, but we cannot say what it is. Feynman would recognize this situation. He spent years developing quantum electrodynamics, a theory so successful it predicts phenomena to 1 part in a trillion. But he also knew that QED, for all its success, doesn't explain why particles have the masses they do, or why the coupling constants have their specific values, or what happens at extremely short distances where the theory breaks down. Success in one domain doesn't mean understanding is complete. The dark matter problem is physics confronting its limits. We've measured something carefully. We've characterized its properties extensively. We've constructed frameworks to explain it. But the fundamental nature of the phenomenon eludes us. The instruments can't reach it. The experiments can't trap it. The mathematics can't fully capture it. This is where science operates at its edge, not in the realm of facts and equations that work, but in the realm of facts and equations that almost work, that point to something just beyond our grasp. Newton's laws almost work for galaxies. They just need additional mass. Einstein's relativity almost works. It just needs modification at low accelerations. Dark matter almost fits. We just can't detect it. Modified gravity almost fits. It just has trouble with galaxy clusters. Almost is where the next breakthrough lives. Almost is where the current framework shows its cracks. Almost is where reality is revealing that our concepts are incomplete. Galaxies rotate wrong. That simple fact, observed in spectrum after spectrum, galaxy after galaxy, for 50 years, remains unexplained. The explanations we have, dark matter or modified gravity, are incomplete, speculative, or both.
Neither has achieved the status of established physics. Neither has earned the confidence that Newton's laws once held, or that general relativity holds in the domains where it's been tested. We're living through an extended period of uncertainty about something fundamental. That's unusual in physics. Most major problems get resolved within a generation. The galaxy rotation problem has persisted for 3 generations of astronomers. The answer appears to be close. We have frameworks, we have candidates, we have experiments running, but close isn't the same as solved.
What would it mean if dark matter is real? It would mean the universe is stranger than almost anyone imagined. It would mean most of what exists is invisible to us, knowable only through gravity. It would mean we're an even smaller part of cosmic reality than we thought. It would vindicate decades of theoretical and experimental effort. It would open entirely new fields of particle physics and cosmology. What would it mean if gravity is modified? It would mean Newton and Einstein saw deeply, but not completely. It would mean the inverse square law is an approximation that breaks down at large distances. It would mean our most fundamental theory of spacetime needs revision. It would change how we model cosmic evolution. It would demand new mathematics, new principles, new ways of thinking about how matter and geometry relate. Either answer would be profound. Either would reshape physics. Either would reveal that reality operates in ways we don't currently understand. But there's a third possibility that's even more unsettling. Perhaps both frameworks are wrong. Perhaps dark matter particles don't exist, and gravity doesn't need the specific modifications Mond proposes. Perhaps the rotation curves are telling us something neither camp has considered. Perhaps we need not a new particle or a new equation, but a new concept. Physics has faced such moments before. Before quantum mechanics, physicists thought they were close to a complete understanding of nature. A few anomalies needed explanation: blackbody radiation, the photoelectric effect, atomic stability, but the framework seemed solid. Then experiments revealed that the framework itself was flawed. Matter and energy weren't separate. Particles and waves weren't distinct. Causality wasn't absolute. The entire conceptual foundation had to be rebuilt. The galaxy rotation problem might be signaling something similar. Not a missing piece in the current framework, but a fundamental flaw in how we're thinking about mass, gravity, and cosmic structure. We won't know until we know. Until then, we're left with observations that don't fit our theories, and theories that don't match reality. The astronomers keep observing. The particle physicists keep searching. The theorists keep calculating. The detectors keep running, deep underground, watching for a signal that might never come. Telescopes scan the sky, mapping rotation curves, measuring gravitational lensing, cataloging galaxies that behave normally and galaxies that don't. And galaxies keep rotating wrong. The stars at the edges keep orbiting too fast. The velocity curves stay flat. The discrepancy remains. The universe continues to do what our best theories say it shouldn't. That's where we are. 50 years into the search for dark matter, 50 years into modifying gravity, and the question Vera Rubin posed when she pointed her spectrograph at Andromeda remains unanswered. Why do galaxies rotate wrong? What are we missing? What is most of the universe made of? Physics doesn't have the answer yet, and until it does, every time we look at a galaxy, whether through a telescope or in a photograph, we're looking at a mystery, a structure held together by something invisible, something we've named but never seen, something that might be matter, might be modified geometry, might be something we haven't conceived of yet. The search continues because the question demands it, not for practical reasons. Dark matter doesn't affect daily life, doesn't change how machines work or how chemistry proceeds, but for fundamental reasons. Because understanding reality means understanding what reality is made of. Because incomplete knowledge is always temporary. Because mysteries exist to be solved, even when the solution takes longer than expected. Feynman would have appreciated the situation. He'd have insisted on clear thinking, careful experiments, and intellectual honesty about what we do and don't know. He'd have pushed against premature certainty, against claiming to understand what we only half understand. He'd have reminded us that not knowing is a stage in the process, not a failure of it. And he'd keep asking questions. Why this acceleration threshold in Mond? Why hasn't any detector found WIMPs? What do the rotation curves actually tell us versus what we're reading into them? What assumptions are we making unconsciously? Where might we be wrong? Those questions remain live, the answers remain uncertain, and galaxies, indifferent to our theories, keep rotating exactly as they do, wrong by our calculations, right by their own existence, mysterious in their mechanics. The universe isn't obligated to make sense to us. It isn't obligated to fit the frameworks we construct. It operates according to principles that might be comprehensible or might be forever beyond our grasp. Our job isn't to force reality into our concepts. Our job is to adjust our concepts until they match reality. We haven't done that yet for galaxies. The concepts don't match. The equations don't close. The observations don't align with the theory. Something fundamental is missing from our understanding. What that something is remains the most important unsolved problem in astrophysics. And until we solve it, every spiral galaxy we observe, every velocity curve we measure, every gravitational lens we map, carries the same implicit question. What is holding you together? What are you made of? Why do you rotate the way you do? The galaxies aren't answering, not yet. They just keep spinning, held by forces we cannot see, composed of matter we cannot name, defying predictions we once trusted, waiting for us to understand.